We've discussed potential energy, we've discussed kinetic energy, we've discussed work, the force acting on an object across a distance that operates as a mechanism of energy transfer. So we need to talk about situations now where an object under the force of gravity is going to undergo a change in energy, where gravity is going to be the mechanism of energy transfer. We already know that if you lift something up above the ground, you're doing work against the force of gravity. You have to lift up, counteracting the force of gravity acting down. And as you do that, you give the object some amount of energy. You do work on it, you give it potential energy. And we said that that potential energy could be calculated as the mass of the object times the acceleration of gravity times the height above ground. And this essentially works out to be the same as the weight multiplied by the height, which is equivalent to work. The force you exert lifting something up at a constant velocity, the minimum required to have it go up and not eventually accelerate back down, multiplied by the distance which you lifted. Weight times height gives us potential energy due to gravity. However, once an object is up above ground, it has the tendency to want to accelerate. So we said it's potential energy because it has the potential to go into motion. Something else wants to do work on it. We refer to this as stored energy, but it's not stored energy like something in a bottle. It's more like it has the ability to have work done on it once it goes into motion. So that potential energy can be utilized. It can turn into energy of motion when the object is released. And we have the equation for kinetic energy down below here, that if you were to exert a force on an object over some distance, you give energy to it. And if it's in a situation where it's accelerating as a result of that force, we say that you've increased or decreased its kinetic energy. So what if gravity is doing all of this work for us? What if we put something up above ground, we release it, and then it falls down? We would say that gravity does work, and gravity is going to be the mechanism of energy transfer that's going to take the potential energy that the object had and convert it into kinetic energy. Now, we can take this and we can pretty much just roll with it, but we want to be able to look at it from the point of view of a big idea, a big formula that we can plug things into and that we can use to solve problems that may otherwise seem to be pretty complicated. Which is going to lead us to the idea of conservation of energy. We can calculate out and say that if something has some potential energy, that gravity is going to do work on it across that drop height if it's released, and then that work goes into changing kinetic energy and call it a work energy theorem. But if we're doing that over and over again, it seems like we're going to be doing multiple steps that always yield the same result. That result ends up being the equation we have on the screen here, the conservation of energy equation. I call it the big idea equation because it encompasses a lot of different ideas in one place. But we would say that in an isolated system, some place where gravity is going to be affecting the object, but it's not being affected by air resistance, friction, there's no other people pushing or pulling, anything that is going to cause it to go into motion in the direction of its motion is only going to be gravity. If that's the case, we can use the equation I got down below that says the total energy initially of the system has to equal the total energy after the work is done on it. So energy is conserved as a total, but it can transfer between the two different types. We can start with a lot of potential and little or no kinetic, but as we lose potential, as we get moved closer to the ground, gravity's doing work on us, which is going to raise our kinetic energy. But the total has to stay constant. So if we expand that a little bit, the big idea equation, we can say that the potential plus the kinetic before gravity does work has to equal the potential plus the kinetic after. It's not that part of an equation actually, but we need to make sure that we keep track of what's going on. So I have two questions that we should ask ourselves for the initial and the final conditions of an object that's going to have work done on it by gravity. Let's make a note of that right here. Questions to ask, and these are questions for both initial and final situations. And those questions are, can the object move to a lower position? So is it up above wherever we're calling our zero level, remembering the potential energy is calculated from some zero and how many meters up we go from there. So is the object able to move to a lower position? If the answer to that question is yes, go ahead and pre-populate a yes and a no. If the answer to that question is yes, that means we're going to keep potential energy in that initial side of the equation. We could have potential and kinetic energy. We could have something above ground and moving. That's not unheard of. Birds do it all the time. So if the object is above ground or above our zero position, and we ask ourselves, is it able to move to a lower position? If the answer is yes, we keep the PE. If the answer is no, then we can cross it out. Now, eventually you just kind of get used to this, and you know, and you just say, well, I'm just going to write PE down because I know it exists and I won't even bother writing it. But to start out with, we want to write it out as a possibility and then cross it out if we're pretty sure that it's not there. Then we can ask ourselves also in the beginning, is the object in motion? Yes or no? I think you can see where this one's going. If the object is in motion, then we're going to keep the kinetic energy. And if the object is not in motion, we cross out the kinetic energy. Oops, not cross off, cross out. I guess we'd cross it off, but Xing it out. And I'll tend to use red and green here to denote that as well. And of course, the big reason is, I don't want to be too pedantic here, but potential energy is equal to mass times gravity times height. So we're concerned with whether or not there is a height value. If the height is zero, there's no potential, so mathematically it would be gone. Same thing for kinetic energy. The quantity that we're concerned with for calculating kinetic energy is velocity. If there's no velocity, it's zero, so 1/2 m times 0 squared is 0, it disappears. So mathematically those things would be 0 if there's no height and there's no motion. Now, again, we need to make sure we ask ourselves these questions for the before and the after, and that way we can simplify the equation. And once we get that simplified, then we can plug in the formulas and we can put in the numbers. We can put in these MGHs and 1/2 mv squareds. So let's take a look at one problem and see if we can utilize this big idea equation with these questions in order to solve it. Before I even read the problem though, I'm going to go ahead and write in the formula, the big idea. PE plus KE initial, I'll just write an I for initial, has to equal PE plus KE final. So let's take a read of it. It says a 50 kilogram skater drops in on a ramp from 6 meters above the ground. How much kinetic energy does a skater have halfway down the ramp? Setup, no calculations. We just want to do the setup here. I've already got a picture drawn showing that the skateboarder is at the top initially, and then the final, of course not absolute final, but for the problem that we're looking at, the final situation is the skateboarder is halfway down the ramp. So we ask ourselves the questions. Is the skateboarder able to move to a lower position in the beginning at this initial point? Yeah, obviously they're 6 meters above the ground. Are they in motion at that point? Generally, skateboarders fall down, and when you fall, you start from rest. So no, there's no kinetic energy in the beginning. We ask ourselves, in the end, the final scenario for our particular problem, is a skateboarder able to move to a lower position? Yeah, they're still 3 meters above ground. They can still fall down 3 more meters. Are they in motion? Probably. If you're halfway down a skateboard ramp, you usually don't stop. So in this case, we would have potential energy in the beginning, all potential. Gravity is going to do some work transferring some of that potential energy into kinetic, but not all of the potential is gone yet. There's still some potential energy. So in that case, we could actually substitute in now values if we knew all of the values, which, I mean, we do, but we're not going to calculate it. But we can put in the formulas. M times G times HI for the initial has to be equal to M times G times H final plus 1/2 times M times V final squared. Now in terms of what's unknown in this problem, it'd be the final velocity. So we could apply some algebra, we could plug in numbers for G and the M's and all that stuff, we can calculate it. If you're savvy, you might notice here that all the terms have M. which means you could cancel out m. You don't even need to know it, but try this, see what you get as an answer. But let's take a look at a second example for the setup and the execution before we take a look at any sort of mathematics. In this case, same skateboarder, I'm sorry, different skateboard, it says 40 kilograms, is moving at 5 meters per second at the bottom of a ramp. How far up the ramp will the skateboarder go? So now it's a little bit different. If we write out that equation, potential energy and kinetic energy in the beginning has to equal potential energy plus kinetic energy in the end. Typo. We ask ourselves those questions, those big idea questions. At the bottom of the ramp, initially, can the skateboarder move to a lower position? No, they can't. They're already at the bottom of the ramp. The ramp disappeared and there's a hole in the ground maybe, but that's not the case. It says they are moving at 5 meters per second, so that means they are in motion. They do have kinetic energy. And we ask ourselves those two questions again at the end. For the final scenario, when they go up the ramp, are they able to move to a lower position? Yes or no? And are they in motion? So if they've gone up the ramp, well, yeah, they're up above ground. That's what we want to figure out. We want to be able to calculate the height above ground that they've made it to. Now, in this case, we'll talk a little bit about it in a second, but be mindful of work. The last question we ask ourselves is the object in motion? Well, if you've gone as high as you can go up a skateboard ramp, you're not going any higher. You haven't fallen back down yet. You're not going up, you're not going down. That means you're not going, you're not moving. So in this case, there is no kinetic energy at the end. We got a fairly simple problem then. We have a scenario where we have 1/2 mass times initial velocity squared is all going to equal mass times gravity, gravitational acceleration times the final height. And that final height is what we don't know. It's a little bit easier to solve, and we're going to go ahead and do that mathematically. But I want to point out here the idea of work being done. As the skateboarder is going up the ramp, if there's someplace in the middle there, as they're moving uphill, that's their displacement. They got a little delta x going up. The force of gravity, on the other hand, is pointing downhill, or a component of the force of gravity is pointing down. The force of trying to slow them is working directly against them. So if we're thinking about lefts versus rights, opposing things, that force going the opposite direction is going to be negative. It's going to be working against them. It's going to be taking away energy instead of adding energy. In this case, taking away kinetic energy as the object moves uphill. So let's go ahead and calculate out what we get for an answer here. I can put in the numbers. Now again, mass does cancel out, but I don't want to actually cancel it out. I want to go and do it with all the numbers. I'd have 40 kilograms, I'd have 5 meters per second, the quantity squared. I'd have 40 kilograms, we're using 10 meters per second squared for the acceleration of gravity. And we have the height is an unknown. The unknown, sorry, I stumbled on my words there. So if we've got, this would be 20 times 25, right? 20 times 25, right? 5 squared. So let's go ahead and get that calculated. I'd like to apologize. There was a glitch in my recording and I got through all the calculations before I started recording, but you can take a look at the math and see where the numbers come from. But as the skater moves up the ramp, gravity is going to be working against their motion, taking away some of their kinetic energy and turning it into potential energy. So again, gravity is going to be that mechanism of energy transfer as the skater goes up the ramp. Now we can continue this with a whole lot of other calculations. We can take a look at the answer for the problem up above. Let's go ahead and see what that looks like. You see here we already got the numbers in. Now it's just a matter of number crunching. We can see where all the numbers go and see what that final answer is. And there we go. We got all the answer right there, so we can apply just our basic algebra skills. We can get the whole numbers moved over, solve for v, and we get a velocity of 7.75 meters per second. So falling 3 meters gets a 7.75 meters per second of velocity. And if we only had 5 meters per second at the bottom, well, then we're not going to be able to move up 3 meters. We only move up 1.25. So that's a look at some of the conservation of energy problem setup. Big idea though, is that we've got this relationship of total energy beginning has to equal total energy in the end. We have to ask ourselves these questions to do the setup. If you get the setup wrong because you don't know what you're doing, the math doesn't matter, all right? So make sure you're getting the setup right and you should be good.